Write the value of limit x tends to 0 root over 1 minus cos 2x upon x. We know that 1 minus cos theta is equal to 2 sin square theta by 2. So we can write 1 minus cos 2x can be written as the limit x tends to 0 here root over 2 sin square 2x by 2, that is x, divided by x, which is equal to limit x tends to 0 root 2 into square root of sin square can be taken as mod sin x, because it can be positive or negative, depends upon its value, upon x. Now let us apply the left limit and right limit. Let us take the left limit. Limit x tends to 0 minus root 2 mod of sin x upon x, which is equal to, for x less than 0, it will, mod of sin x is negative. So let me write here mod of sin x is equal to plus sin x when x is greater than 0 and negative sin x when x is less than 0. So we can write for the left limit it is less than 0. So root 2 limit x tends to 0 root 2 into minus sin x upon x, which is equal to limit x tends to 0 negative root 2 times sin x upon x. And since we know that limit x tends to 0 sin x upon x is 1, so we can write negative root 2 into 1. So the answer is minus root 2. And now coming to the right hand limit. Right limit x tends to 0 plus root 2 mod of sin x upon x, which is equal to limit x tends to 0 root 2 when x is positive, means above 0, right limit means above 0, mod of sin x can be taken as plus sin x upon x, which is equal to root 2 into limit x tends to 0 sin x upon x. Since we know that limit x tends to 0 sin x upon x is 1, so we can write root 2 into 1, which is equal to root 2. So we can observe that the right limit and left limit both are not equal. So we can write left limit is not equals to right limit. Hence we can conclude that limit x tends to 0 root over 1 minus cos 2x upon x is does not exist. So the answer is does not exist. Okay. Write the value of limit x tends to 0 minus step x. It's a greatest integer function. Limit x tends to 0 minus step x. Since we know that limit x tends to a minus f of x is equal to, we can write it as limit h tends to 0 f of a minus h. So we can write here limit h tends to 0 step of 0 minus h. So that is limit h tends to 0 step of minus h. Here minus h lies between minus 1 and 0 because it is below 0. So step of minus h will be taken as minus 1. Since we know that for x lies between 0 and 1, step x is equal to 0. For x lies between minus 1 and 0, and even including here. So we can write step x is equal to minus 1 when it is below 0. So we can give the answer minus 1. So we can write here limit h tends to 0, step of minus h value will be minus 1. So the answer minus 1 because it's an independent of h. So the value of limit x tends to 0 minus step x value is minus 1. Write the value of limit x tends to 0 plus step x. It's a greatest integer function, step x, and since we know that limit x tends to a plus f of x, we can write it as limit h tends to 0 where h is positive, limit h tends to 0 f of a plus h where h is very small and it's positive. So we can write here limit h tends to 0 step of 0 plus h, and h is positive and it's a 0 plus h. So we can give limit h tends to 0 step of h where h lies between 0 and 1. H lies between 0 and 1. So we can write step h can be taken as 1 since for x lies between 0 and 1, step x is equal to 0. Sorry, we can write here 0. Step h is equal to 0. So we can give the answer limit h tends to 0 and it's a 0. So the answer is 0. So the value of limit x tends to 0, step x is 0. Okay. Write the value of limit x tends to 1 minus x minus step x. It's the greatest integer function. Since we know that limit x tends to a minus f of x, we can write it as limit h tends to 0 f of a minus h. So we can write here in terms of h where h is a very small quantity and it's positive. So limit h tends to 0 f of a minus h, that is 1 minus h minus of step of 1 minus h. In place of x we can substitute 1 minus h, a minus h, a is equal to 1 here. So we can write limit h tends to 0 1 minus h minus, and for h is very small positive value since h lies between 0 and 1. So we can write minus h lies between minus 1 and 0, and 1 minus h lies between 0 and 1. Since 1 minus h lies between 0 and 1, so step of 1 minus h value will be taken as 0. So we can consider step of 1 minus h value is 0. So as limit h tends to 0, so we can add 1 minus, in place of h we can substitute 0. So the answer is 1. So the value of limit x tends to 1 minus x minus step x is 1. Write the value of limit x tends to 0 minus sine of step x upon step x. It's a greatest integer function, step x. And since we know that limit x tends to a, f of x is equal to, so limit x tends to a minus f of x is equal to limit h tends to 0 f of a minus h. So we can write limit h tends to 0 here, sine of 0 minus h, step of 0 minus h upon step of 0 minus h, where h is a very positive, very small positive quantity, and h lies between 0 and 1. Then negative h lies between minus 1 and 0, and step of minus h value is minus 1. So we can write here limit h tends to 0 sine of step of minus h, that is sine of minus 1, divided by 0 minus h, that is a step of minus h is minus 1. So we can write limit h tends to 0 minus sine 1 upon minus 1 So which is equal to limit h tends to 0 sine 1. So here sine 1 is independent of h, so we can write direct answer sine 1. So sine 1 is the answer for the limit. Okay. Write the value of limit x tends to pi sin x upon x minus pi. So we can write here as, since sin pi minus x is equal to sin x, because the second coordinate sign is positive, so we can write here limit x tends to pi sin of pi minus x we can write divided by negative of pi minus x. X minus pi we can also write it as minus of pi minus x. Limit x tends to pi, or we can write x as x tends to pi, h tends to 0 where h is equal to pi minus x. When consider h is equal to pi minus x, so we can write h tends to 0 sin pi minus x we can write sin h upon minus h. So that is limit h tends to 0 minus 1 into sin h upon h. And since we know that limit x tends to 0, theta tends to 0, sin theta upon theta is equal to 1. So we can give the answer minus 1 into limit h tends to 0 sin h upon h is 1. So minus 1 is the answer. So limit x tends to pi sin x upon x minus pi value is minus 1. Okay. Write the value of limit x tends to infinity sin x upon x. As x tends to infinity, 1 upon x tends to 0. So let us consider 1 upon x is equal to h. So h tends to 0 where h is positive here. So we can write the limit as x tends to infinity, h tends to 0 sin x is equal to 1 upon h. We can write sin of 1 upon h divided by 1 upon h. So we can also write this as limit h tends to 0 h times of sin of 1 upon h. And since we know that as h tends to 0, sin 1 upon h value is a finite oscillating number. It's a finite oscillating number between minus 1 and plus 1. So it is a finite value. So we can give the answer. So it is limit h tends to 0 h into limit h tends to 0 sin of 1 upon h. So this value we can get a finite value between minus 1 and plus 1. And limit h tends to 0, h is nothing but 0. So 0 into some finite value, answer is 0. So we can give the answer for this question. Limit x tends to infinity sin x upon x is 0. Okay. Write the value of limit x tends to 2 mod of x minus 2 upon x minus 2. Since we know from the definition of mod x is equal to x when x is greater than or equals to 0 and minus x when x is less than 0. So as mod of x minus 2 we can write it as x minus 2 when x is greater than or equals to 2 or minus of x minus 2 when x is less than 2. So we can write here limit x tends to 2 minus mod of x minus 2 for left limit, and right limit x tends to 2 plus mod of x minus 2 upon x minus 2. So this problem is based on above 2 and below 2. So if it is above 2, we have x minus 2, and below 2 mod is minus of x minus 2. So left and right limit. So we can add here limit x tends to 2. Mod of x minus 2 we can write it as negative of x minus 2 because it is below 2 divided by x minus 2. And for the right limit we have limit x tends to 2 plus the limit x tends to 2. Modulus of x minus 2 it will be positive. So we can add x minus 2 upon x minus 2. So here x minus 2 get cancelled. So we had minus 1 as limit x tends to 2 minus 1 is constant. So minus 1 here, and limit x tends to 2 here also x minus 2 get cancelled, and here it is 1. So here left hand limit and right hand limit both are not equal. So left hand limit is minus 1 and right hand limit is plus 1, both are not equal, and hence we can say limit does not exist. So limit x tends to 2 mod of x minus 2 upon x minus 2 does not exist. Okay. Write the value of limit x tends to 0 sin x degrees upon x. And since we know that limit theta tends to 0, sin theta upon theta is equal to 1 when theta is in radians. So here given x degrees, so let us convert the degrees into radians, and as also we know pi radians is equal to 180 degree, or 1 degree is equal to pi by 180 radians. So x degree is equal to pi by 180 radians into x. So we can write limit x tends to 0 sin x degree, we can write it as x into pi by 180 radians upon x. So let us multiply and divide with pi by 180. Pi by 180 here, and again pi by 180. So as x tends to 0, pi by 180 into x also tends to 0. So let us consider this as some h or something. So sin h upon h is, as h tends to 0, sin h upon h is 1. So we can write here limit or something p tends to 0 sin p upon p into pi by 180, where p is equal to pi by 180 into x radians. So as p tends to 0, sin p upon p is 1, so 1 into pi by 180. So the answer is pi by 180. Pi by 180 is the answer. Okay. Write the value of limit x tends to 0 minus sin x upon root x. And we know that limit x tends to a minus f of x is equal to limit h tends to 0 f of a minus h, we can write. So which is equal to limit h tends to 0 sin of 0 minus h upon root over 0 minus h, where h is a positive, small positive quantity. So we can add here sin of minus h limit h tends to 0, sin of minus h is minus sin h upon square root of minus h. Since h is positive, so minus h is negative, so root over minus h is not defined in real numbers, so we can say that limit h tends to 0 minus sin h upon root over minus h does not exist. Since root over minus h does not belongs to R. Okay. Write the value of limit x tends to 0 sin x upon root over 1 plus x minus 1. So let us rationalize the denominator here. Multiply and divide with root over 1 plus x plus 1 upon root over 1 plus x plus 1, which is equal to limit x tends to 0 sin x into root over 1 plus x plus 1 upon root over 1 plus x plus 1 into root over 1 plus x minus 1 can be taken as root over 1 plus x whole square minus 1 square. So which can be written limit x tends to 0 sin x into root over 1 plus x plus 1 upon, here we can write root over 1 plus x minus 1. So which is equal to limit x tends to 0. So we can write sin x upon x into root over 1 plus x plus 1. So by using the properties of limits, we can write limit x tends to 0 sin x upon x into limit x tends to 0 root over 1 plus x plus 1. And since we know that limit theta tends to 0, sin theta upon theta is equal to 1 with theta is in radians. So we can write limit x tends to 0 sin x upon x is 1 into, when you substitute here x is equal to 0, we have 1 root over 1 plus 0 plus 1. So that is root 1 is 1, 1 plus 1 is 2. So 1 into 2, so the answer gives 2. Okay. Write the value of limit x tends to minus infinity 3x plus root over 9x square minus x. So as x tends to minus infinity, so minus x tends to infinity, then minus 1 upon x tends to 0. Let us substitute y is equal to minus 1 upon x. So as x tends to infinity, y tends to 0. So we can change the limit. Limit x tends to minus infinity can be written as limit y tends to 0 3 times of, and x is nothing but, so x is equal to minus 1 upon y. Let us substitute here. So we can add minus 3 upon y plus root over 9 times of minus 1 upon y whole square minus of minus 1 upon y. So we can write this as limit y tends to 0 minus 3 upon y plus root over 9 divided by y square plus 1 upon y. So which is equal to limit y tends to 0 minus 3 upon y plus, we can take LCM, y square is LCM, and here 9 plus y under root of. So limit y tends to 0 minus 3 plus root over 9 plus y upon square root of y square is y, so we can take y. So let us rationalize it. Minus 3 minus root over 9 plus y upon minus 3 minus root over 9 plus y. So which is equal to limit y tends to 0. In the numerator it is in the form of a plus b into a minus b, so we can simplify it as minus 3 whole square minus root over 9 plus y whole square upon y into, or you can take minus y times of 3 plus root over 9 plus y. So in the numerator we can write limit y tends to 0, it is 9 minus of 9 plus y upon minus y times of 3 plus root over 9 plus y. So which is equal to limit y tends to 0, 9 minus 9, it's a 0 and negative y upon minus y times of 3 plus root over 9 plus y. So we can cancel negative y in the numerator and denominator. So we had limit. So let us substitute the limit here. Limit y tends to 0, so we can write 1 upon 3 plus root over 9 plus 0, that is 1 upon 3 plus root 9 is 3, so 1 upon 3 plus 3 is 6. So we can go with an answer 1 upon 6 for this limit. Okay. Write the value of limit n tends to infinity n factorial plus n plus 1 factorial upon n plus 1 factorial plus n plus 2 factorial. So which is equal to limit n tends to infinity n factorial plus n plus 1 factorial, we can write it as n plus 1 into n factorial upon n plus 1 factorial in the denominator, n plus 1 into n factorial, and n plus 2 factorial we can write n plus 2 into n plus 1 into n factorial. Just like 5 factorial is equal to 5 into 4 factorial we can write, or we can also write 5 into 4 into 3 factorial. So as n plus 2 factorial and n plus 1 factorial we can split accordingly, and then limit n tends to infinity, we can take out n factorial common. So we have 1 plus n plus 1 in the numerator, and in the denominator n factorial taken common, and even n plus 1 also taken common. So we have 1 plus n plus 2. So which is equal to limit n tends to infinity, n factorial gets cancelled, and hence we can add 1 plus n plus 1, that is n plus 2 in the numerator, and in the denominator n plus 1 into n plus 3 we can write. So let us take common n in the numerator. So we had 1 plus 2 upon n, and in the denominator if I take one n common here, 1 plus 1 upon n, and again if I take n common here, 1 plus 3 upon n. Since limit as n tends to infinity, 1 upon n tends to 0. So limit n tends to infinity, 1 upon n value is 0. So we can cancel here n, and then we can apply this limit. So 1 plus 2 into 1 upon n, that is 0 upon, so here it is 1 plus 0, and again here 1 upon n. So this 1 upon n can be taken as 0 into 1 plus 0. So finally we can say that 0 into 1 upon 1, it's a 0. 0 is the answer. Okay. Write the value of limit x tends to pi by 2, 2x minus pi upon cos x. So we can write this as limit x tends to pi by 2. By taking minus 2 common, I can write this as numerator pi by 2 minus x upon cos x, we can also write it as sin pi by 2 minus x. So which is equal to minus 2 times of limit x tends to pi by 2, pi by 2 minus x upon sin of pi by 2 minus x. So for our convenience, let us consider pi by 2 minus x is equal to h. So as x tends to pi by 2, h tends to 0. So we can change the limit minus 2 times of limit h tends to 0, h upon sin h, or we can also write minus 2 times of limit h tends to 0, 1 upon sin h upon h. And since we know that limit theta tends to 0, sin theta upon theta is equal to 1. So we can give the answer here minus 2 into 1 upon limit h tends to 0, sin h upon h value gives 1. So 1 upon 1. So the answer is minus 2 for the limit. Okay. Write the value of limit n tends to infinity, 1 plus 2 plus 3 plus and so on up to n upon n square. Since we know that sum of first n natural numbers 1 plus 2 plus 3 plus and so on n is equal to n into n plus 1 by 2. So we can write here limit n tends to infinity n into n plus 1 upon 2 n square. So we can write here limit n tends to infinity. If I take n again common, n into n times of 1 plus 1 upon n divided by 2n square. So we can cancel here n and n square. So we had limit n tends to infinity 1 plus 1 upon n divided by 2. So as n tends to infinity, 1 upon n tends to 0. So we can give the answer here 1 plus 0 upon 2, that is 1 upon 2. So 1 upon 2 is the answer. 1 upon 2 is the answer for the given limit. Okay.